For more than a century, humanity has built bridges so massive they almost seem impossible. Some rise higher than the Eiffel Tower. Others stretch so far the horizon itself disappears. But the most terrifying part is this. These gigantic structures are never truly still. Beneath the wind, earthquakes, ocean currents, and the relentless weight of time, they are constantly moving. Steel bends, cables vibrate, foundations shift silently beneath the waterline, and most of it happens invisibly, far beyond what the human eye can see. Because the greatest bridges on Earth are not only fighting traffic, they are fighting wind, corrosion, gravity. Mila Viaduct, the bridge above the clouds. At sunrise in southern France, the Mila Viaduct slowly emerges from the fog, like something built by another civilization. Its tallest tower rises higher than the Eiffel Tower itself. But what makes this bridge feel impossible is not its height. It is the feeling that the structure barely touches the earth at all. The bridge was built to solve massive traffic congestion through the Tarn Valley. But once construction began, engineers realized traffic was not the real challenge. Wind was. The valley acts like a giant natural wind tunnel. As air accelerates through the canyon, enormous lateral forces begin pushing against the structure. And because the bridge is incredibly thin and lightweight, movement becomes unavoidable. The steel deck was intentionally designed to remain flexible enough to move safely under extreme loading. As wind flows across the bridge, vortex-induced vibrations begin forming. Oscillations spread through the cables. Cyclic stresses move through the entire structure. If damping systems fail to control those forces, fatigue slowly begins accumulating deep inside the connections. And that is what makes bridge engineering so unsettling. Bridges rarely fail instantly. Most of them deteriorate silently for years before anyone realizes something is wrong. Akashi Kaikyo Bridge, built to survive the earthquake. Japan's Akashi Kaikyo Bridge was never designed for calm conditions. It was designed with the assumption that nature would eventually strike it with catastrophic force. Construction began in the late 1980s with one goal: to build the longest suspension bridge span on Earth. Its central span stretches nearly 2 kilometers across open water. But in 1995, disaster struck. The Kobe earthquake shook the region violently. The ground beneath the bridge shifted. The distance between the towers changed by nearly 1 meter. Many engineers believed the project had failed, but the bridge survived, and that moment transformed Akashi into an engineering legend. A suspension bridge survives through an incredibly efficient load path. Traffic loads enter the deck, travel into suspenders, then into the massive main cables, before transferring down into the towers and anchorages. But on a bridge this large, traffic is no longer the greatest threat. Movement is. Wind, earthquakes, aerodynamic instability. If oscillations exceed design limits, internal stresses begin building rapidly through the structure. That is why Akashi relies on aerodynamic deck shaping, deep caisson foundations, massive damping systems, and thousands of structural sensors constantly monitoring movement every second. Because modern bridge engineering no longer assumes nature will be gentle, it assumes nature will eventually exceed expectations. Hong Kong, Zhuhai, Macao, the megastructure across the sea. From above, the Hong Kong-Zhuhai-Macao crossing no longer looks like a bridge. It looks like an artificial world built across the ocean itself. More than 55 kilometers long, the project connects bridges, artificial islands, and underwater tunnels into one continuous megastructure. And every part of it exists because of a compromise between impossible forces. Cargo ships needed clearance. Airplanes needed open flight paths. The ocean itself constantly pushed against the foundations below. So engineers did something extraordinary. Part of the structure disappears beneath the sea floor through an immersed tunnel system hidden underwater. And beneath the surface, another invisible threat begins attacking the structure every second. Scour. Ocean currents slowly remove soil surrounding the foundations. As that soil disappears, lateral stability weakens, foundation demands increase, and structural stresses begin redistributing through the bridge. The terrifying part is that most of this happens completely out of sight, below the waterline, where almost nobody can see it happening. The bridge must also survive saltwater corrosion, ship collisions, typhoons, fatigue, and thermal movement across enormous distances. Because modern bridge engineering is no longer only about preventing failure, it is about making sure failure does not become catastrophe. Golden Gate Bridge, the icon that never stops fighting. The Golden Gate Bridge is more than a symbol of San Francisco. It is a symbol of human ambition during one of the hardest periods in American history. Construction began during the Great Depression, when millions of Americans were unemployed and many believed building a suspension bridge across the Pacific winds was impossible. But only 4 years later, the bridge stood complete. Even its famous international orange color serves a purpose beyond appearance. It improves visibility through heavy fog while helping protect the structure from the harsh marine environment. The bridge follows the classic suspension bridge load path: deck, suspenders, main cables, towers, anchorages. A nearly perfect system for distributing force. But the bridge's greatest enemy is not traffic, it is time. Salt-filled air from the Pacific constantly attacks the steel structure. Corrosion does not create instant disaster. Instead, it weakens the bridge slowly through fatigue, crack propagation, and gradual section loss. That is why maintenance on the Golden Gate Bridge never truly stops. Inspection, painting, monitoring, repair. Because once a bridge is completed, the longest battle has only just begun. Danyang Kunshan Grand Bridge, the bridge with no end. Driving across the Danyang Kunshan Grand Bridge feels strangely unreal. The bridge stretches so far into the distance, it almost seems endless. At nearly 165 kilometers long, it remains the longest bridge on Earth. And unlike most megabridges, this one was built for high-speed rail, which makes the engineering far more unforgiving. At extreme speeds, even tiny alignment errors can become dangerous. A deviation of only a few millimeters may increase vibration, amplify dynamic loading, and create derailment risk. But one of the greatest threats comes from something almost invisible: temperature. Massive bridge segments continuously expand and contract as temperatures change throughout the day. Those movements must be controlled through highly complex expansion systems spread across the structure. If those systems fail, internal stress begins accumulating, alignment slowly changes, fatigue starts forming deep inside critical connections. Large sections of the bridge also cross weak soil and swamp regions, and if settlement occurs unevenly, the entire rail system begins losing precision. The terrifying part of engineering at this scale is that there is almost no room for error at all. Øresund Bridge, the bridge that vanishes into the sea. Out in the Baltic Sea, the Øresund Bridge suddenly disappears. Not because of fog, not because of distance, but because the bridge literally descends beneath the water itself. What began as a bridge between Denmark and Sweden eventually becomes an underwater tunnel hidden below the sea floor. And the reason was surprisingly simple: airplanes. If the bridge continued any higher, it would interfere directly with flight paths into Copenhagen Airport. So engineers were forced to do something extraordinary. Halfway across the ocean, the bridge dives underground, and that transition became one of the most difficult engineering problems in the entire project. At the connection between the bridge, the artificial island, and the submerged tunnel, multiple forces begin colliding at once: settlement, water pressure, thermal movement, corrosion. If waterproofing systems begin failing over time, seawater can slowly penetrate the structure itself. And yet, most people driving across Øresund never even realize the exact moment the bridge disappears beneath the sea. That is the strange beauty of great engineering. The most complicated systems on Earth are often the ones people barely notice at all. Russky Bridge, built against the Siberian winter. At first glance, Russia's Russky Bridge looks impossibly thin, but this bridge was built to survive one of the harshest climates on Earth. Winter temperatures here can fall below -40 degrees Celsius. Powerful sea winds strike the structure constantly, and when ice begins forming across the cables, everything changes. Ice loading does not simply add weight, it changes the aerodynamic behavior of the entire cable system. Vibration patterns begin shifting unpredictably through the structure. If those oscillations continue long enough, fatigue cracks can begin forming deep inside critical connections. And the terrifying part is this: failures like these usually begin in places far too small for the human eye to see. That is why modern megabridges are filled with thousands of sensors, monitoring movement, stress, vibration, and microscopic changes happening inside the structure every second. Because bridges this large rarely collapse because of one catastrophic mistake, they deteriorate slowly through thousands of tiny failures accumulating over decades. Sidu River Bridge, the bridge suspended above empty space. Standing on the Sidu River Bridge feels almost unreal. Beneath the roadway lies nearly 500 meters of empty air. The canyon below is so deep, the valley floor often disappears beneath clouds and fog. And building this bridge was a logistical nightmare. The greatest challenge was never the towers, it was crossing the canyon itself. During parts of construction, engineers had only a few hours of stable weather before violent winds returned. To get the first cable across the gap, rockets were launched over the canyon, carrying pilot lines behind them. Only then could the main suspension cables finally be installed. But once the bridge was complete, another danger appeared: wind. As air compresses through the narrow canyon, wind speeds increase dramatically. Oscillations begin forming across the deck and cable system. Cyclic loading spreads through the structure over and over again. And if damping systems fail to control those movements, fatigue slowly begins accumulating inside the bridge itself. Sidu reveals something unsettling about modern engineering. Humanity does not truly conquer nature. It only learns how to survive inside it a little longer. Mackinac Bridge, the bridge that terrifies drivers. The Mackinac Bridge is one of the few bridges in America so frightening many drivers refuse to cross it themselves. The reason lies in the center lanes. Instead of solid pavement, sections of the roadway are made from open steel grating. Drivers can see directly through the bridge to the water far below. And for many people, even a brief glance downward triggers pure survival instinct. But from an engineering perspective, the design is brilliant. The Mackinac Strait experiences violent crosswinds capable of pushing enormous lateral forces against the bridge. If the deck were completely solid, wind pressure across the structure would increase dramatically. So engineers allowed air to pass directly through the roadway itself. And that reveals one of the most important truths in bridge engineering. The larger a bridge becomes, the more it must allow controlled movement. Because a structure trying to remain perfectly rigid against nature can become far more dangerous than one designed to move safely within controlled limits. Sunshine Skyway Bridge, reborn from disaster. On May 9, 1980, disaster struck the original Sunshine Skyway Bridge in Florida. During severe weather, a massive cargo ship slammed directly into one of the bridge supports. Within seconds, a large section of the bridge collapsed into the water below. 35 people were killed. One bus nearly vanished along with the falling deck. It became one of the deadliest bridge disasters in modern American history. But the replacement bridge was not designed simply to replace what had been lost. It was designed around a terrifying assumption that eventually another accident would happen. Engineers redesigned the entire structure with larger foundations, stronger pier protection, safer navigation channels, and far greater structural redundancy. Because ship collisions generate impact forces far more violent than normal traffic loads, modern bridge engineering no longer assumes disaster is impossible. It assumes that sooner or later, something will go wrong. And when it does, the structure must remain standing long enough to prevent total collapse. These bridges are more than steel, concrete, and cables. They are humanity's attempt to resist forces far greater than itself: wind, earthquakes, corrosion, time. But no structure lasts forever. Fatigue accumulates silently. Foundations shift beneath the water. Steel weakens one microscopic crack at a time. And history has shown bridges rarely collapse because of one catastrophic mistake.